We are back, and before we get started on this lesson, if you have the PowerPoint slides, hopefully we're in a good rhythm with using those right now. We are on letter E, the nuclear quantum atom. And you should really record all of those notes, kind of like the last section or a couple lessons ago where it was all those energy definitions. You want to do that here. I don't think there's really much gained here for me to copy all that down. So some of this is pretty simple. You've seen this before, but some of you it's been years, so I don't want to assume anything, and maybe some of you have never seen this. So the nucleus is what's at the center of the atom, and that has the protons and the neutrons, and those are about the same mass. Those are called nucleons combined. Most chemistry textbooks don't call them that, but the nucleons are what's in the nucleus, protons and neutrons, and that makes up most of the mass of the atom. So that's the nuclear part of the atom. The quantum part of the atom that we're going to discuss are the electrons. The electrons are smaller, much smaller by comparison, about 1,000th the mass of nucleons. And they exist outside the nucleus in a series of distinct, sometimes called discrete, that doesn't mean quiet, that means separate unto themselves, or categories of energy levels, starting with energy level 1, energy level 2, energy level 3, and outward. So this is called the nuclear quantum atom. You might remember, and some of you, I'm just going to throw this out there, some of you might remember that 2 electrons can go in the first energy level. How many electrons can go in the second energy level? A lot of people will just say 8. They might not remember what all of that means, but they remember 2 in the first, 8 in the second, and then depending on who you had for a teacher, you might remember what goes in the third. Okay, so those are the basics. So copy down all those definitions. Have your periodic table handy, because ultimately what we want to be able to do after this lesson, I don't know if I'm going to do both of these in one lesson, is we want to be able to dissect an individual atom. So carbon, we'll just use carbon because it's carbon, okay? So we're going to use that as an example. And how do you get all the information about carbon from the periodic table, and what information can't you get? And would you have to be given from another set of data? So this is what you want to do. All right, so I'm going to use carbon as an example for all of these definitions. So if you haven't had a chance to write down all the definitions, atomic number is how many protons there are. Mass number is the protons plus the neutrons, okay? Average, so if you haven't had a chance to do all of that, write all of that down, because I'm just going to use this as an example. Okay. Oh yeah, right. Part of your timeline activity is to redefine the nucleus in terms of quarks. Protons and neutrons can actually break down into smaller particles called quarks. So you can actually have another definition of the nucleus there. But that's part of the other, and that's called the standard model. Okay, so we're just going to stick to a model of the atom that's about 100 years old, but it works very well. All right, so carbon, excellent. Using your periodic table, carbon has an atomic number, sorry, it's kind of dark in here. Carbon has an atomic number of 6. So the atomic number is 6, excellent. So therefore we have 6 protons. Fine. Because we're talking about a carbon atom, not a carbon ion that has a charge, it's neutral. So, therefore, that's a symbol for therefore, we also have 6 electrons. The pluses and the minuses have to be equal in a neutral atom. So we have 6 protons by definition of the atomic number, and because it's a neutral atom, we have 6 electrons. Excellent. Okay, carbon, I think this is on the slide. Yep. Carbon has 3 naturally occurring isotopes. Okay, so symbols P plus, proton, E minus, electron, N0, neutron, no charge. Okay. An isotope it's the same atom, which means same protons, but just different neutrons. So just know that definition. Not all isotopes are radioactive, by the way. Sometimes that word radioactive isotope always gets frequently put in front of this word. Not all isotopes are radioactive, which is good in most cases. So, fine, let's see here. Let's see, as naturally occurring isotopes with 6 neutrons in one isotope, 7 neutrons in another isotope, and 8 neutrons in another isotope. Cool. So another definition that you saw on there is called the mass number. The mass number is the sum total of the protons plus the neutrons. So the mass number for the first isotope would be 6 plus 6, 12. The mass number for the second isotope would be 6 plus 7, 13, and then 14. And we actually call those carbon 12, carbon 13, and carbon 14. So these are the mass number, and that's the number of nucleons. And these are called the isotope names. Nice. And then, so that's one way of writing. So it's carbon 12, carbon 13, carbon 14. So one thing you should do is, if I just write down carbon 14, you know automatically how many protons, because it's carbon, there's 6 protons. You know how many electrons, it's carbon, so there's 6 electrons. And now you know how many neutrons, 14 minus 6, 8 neutrons, 7 neutrons, 6 neutrons. So you can get all that information just from the name. There's another way we often represent this, because this is a bit long to do. These are called isotope symbols. I think you can figure out what we're doing. Atomic number and mass number. Atomic number, mass number. It's always the same for carbon. That should always match up. Okay, these are called isotope symbols. Okay, great. So that's how you name isotopes. Yeah, I guess I was going to put this definition here. I don't think this is on the slides. How do we measure mass on an atomic level? Well, we have something called an atomic mass unit. It's not all that useful for us as chemists, but it's called an AMU. Biologists will often call this a Dalton, after John Dalton, who was a famous chemist who also did some biology. So an atomic mass unit is defined as 1/12 the mass of a Okay, so we use carbon as a standard for measuring lots of things in chemistry. And one thing we do is we use carbon 12, because it's the most abundant isotope. I'm going to show you that in a second. Isotope of carbon, and we use that as a standard. So 1/12 the mass of a carbon 12 atom. That kind of makes sense. That's defined to be 1 AMU. And we use that as a measurement of mass for everything else. So that's why I wanted to show you what that was. Sorry, that's canceling out. All right, so those are the basic definitions. That's fine. The next thing I want to show you is when you look at carbon on the periodic table, it tells you the atomic mass at the bottom of the little element square. What does the element square tell you? It tells you the charges, +4 and -4. We'll get to that. It tells you the atomic number, the element symbol, the name. Yeah, and the atomic mass on carbon is 12.011. Well, that should give you a clue. It's really close to 12. So the atomic mass in the periodic table is really close to this. That's because this has the highest abundance in nature. And now this information that I'm going to give you here is, you would have to be given this information. This is, I don't know what letter it is on here. It's letter 1C, average atomic mass. But this is not, I'm going to say this before I write anything. When you calculate an average atomic mass, you don't take, well, this has 3 isotopes. There could be 13 isotopes. You don't just take them and divide by 3, or take them and divide by 13. You have to take into account what percentage exists in nature. If I just took these and divided by 3, that assumes it's 1/3, 1/3, 1/3 in nature. It doesn't work that way. If there's 5, 20%, 20%, 20%, 20%, I think that's right, yeah. So it doesn't work that way. So these are called weighted average atomic masses based on their percent abundances. This is actually pretty easy to do, so I'm just going to kind of jam through an example, and you can do the math on your own. This is information you would have to be given. I would have to tell you, so for, let's just use symbols, make it faster. This is experimental data. So here's the symbol, which we already know. The mass of the isotope. Now, this is experimental data, so I'm just going to put the subscript EXP, so experimental, if you want to write that out. And this is measured in AMUs, that's why I had to give you that definition. What is that? And then the percent abundance. It's kind of a neat instrument that does this. It's called a mass spectrometer that can actually separate the isotopes, and you get a bigger peak for this, a smaller peak here, and an even smaller peak here. Oh, by the way, this is the radioactive one. Which means its nucleus decays and gives off radiation particles. And that's used in carbon dating. It's not the only isotope used in carbon dating, but it's one of them. Like if you find an organic material, whatever organic matter you have, like a plant or something, or a bone, and you want to date it, you can use carbon-14 to do that. Okay, but that's something else. So for carbon-12, you'll notice that the mass is slightly less than 12. That's actually because there's a distortion of the mass in the nucleus, because the protons and neutrons are held together so tightly with a force called, well, in that case, the weak nuclear force, that it distorts the mass of the overall atom. But that's almost all of it. 98.89% is carbon-12. That's most of the carbon that's in organic material, including you and me. Carbon-13 has an average AMU of 12.9816, and that's much less abundant, 1.11%. And the last one, 13.95. Okay, again, I would give you this data, or have you go to some website where you can click on the element and it will tell you what these data are. There's lots of interactive periodic tables out there. Okay, so let's just cut to the chase. And I'm going to let you do this one. I'll write it out, but you can do it. So the bottom line is this. If you do this problem correctly, you get this answer on the periodic table. That's how it works. If you don't get this answer, you did something wrong. But there's not that much to go wrong here. So here's the basic idea. You can do this one of two ways. If this was a mathematical average, I would take this plus this plus this and divide by 3. That gives you the wrong answer, because that's going to give you an answer around here, which is not the atomic mass of carbon. So the way you do it is you take the mass times the percentage plus the mass times the percentage plus this mass times this percentage, and then to get rid of the percentages, you divide your answer by 100. Or you convert each of these to a decimal place. So you move the decimal place 2, multiply. Move the decimal place 2, and multiply. Move the decimal place 2, might not seem like you would do that, and multiply, and then add all those up. I think it's easier just to do it. Multiply So just multiply those, and then add up the answers. I'm not sure you want to write that there. That's what you do. Okay, go ahead and do that and see if you get the answer on the periodic table. 12.011. So we're going to take 11.9935 AMUs. Let's be precise and use units. Times 98.89. It's not really in units. I'm not going to bother with that. Just put a bracket there. Plus the next one. 12.9816 AMUs times 1.11 plus 13.9511 AMUs times 0.01. Yeah, so multiply each of them successively, add them together, divide by 100, and you should get approximately 12.011 AMU. If you have something slightly different because it rounded or something, don't worry about that. As long as you got about that, then you know you did it right. Fine. Okay. I think I'm going to do one more thing here. Yeah, maybe I'll do a little bit more. Yeah, I'm going to erase some more. Sorry, I'm figuring out a way to word this. Note. Actually, I'm not going to write it. It's going to be kind of awkward. If you go to the periodic table, I think it's easier if I just say it. If you go to the periodic table and you look at the average atomic mass and you round it to the nearest whole number, so carbon, that's easy, it's 12. What is it for nitrogen? Well, it's 14. Oxygen, it's 16. So you round it up or down to the nearest whole number, and that will typically be the mass number of the most abundant isotope. Typically. So, directly from the periodic table, if you round the mass number, you can get the mass number of the most abundant isotope. The atomic number is what it is. So you can get the protons, the electrons, and the neutrons directly off the periodic table for the most abundant isotope. To calculate the average atomic mass, to go the other direction, I would have to give you this information. So that's something I'm going to expect you to be able to do. Okay, I think I will actually keep going here a little bit, but I'm going to need some space because I think it makes sense to finish atomic structure and maybe a little bit about the periodic table here today. Yeah, so let's do that. So if you want to, you can go ahead while I'm fumbling here and erasing. You can go ahead to a couple of slides down, and there's an example where we're doing oxygen, and it gives you some information there. You can start working on the example for oxygen a couple of slides down. You can't do all of it, but there's some of that you can do. You can fill in the atomic number, the mass number, and all that good stuff. And that'll save us some time a little later, so thanks for kind of working with me here. I just have to erase some of this. Actually, I'm going to erase most of it. Okay, so the last thing I want to do is so we've done the nucleus. We haven't really talked about electrons other than how many there are, but where are they located? So I'm just going to do this. It's going to be a little sloppy, but oh no, I erased his message. Okay, so yeah, I guess I'll put this here too, just so you have it. It's kind of interesting. So this is under number 2 from the previous notes, which is about discrete energy levels. Okay, so the protons and the neutrons are in the nucleus. They're held together by what's called the weak nuclear force. I might have put that on the timeline activity. The Quarks are held together by what's called the strong nuclear force, and that is the strongest force known in nature. Now this class we don't go that far into the atom. But now the electrons can't be broken down into anything smaller. Those are what are considered fundamental particles. And they are much smaller, but for chemistry, they're perhaps the most important of the three subatomic particles. Just to give you an example, so protons, neutrons, electrons, how much do these things weigh? It's amazing, I think, we can determine the mass of an individual proton or neutron in grams, but we can. And we define an AMU to be 1/12 the mass of carbon-12. So it's not surprising that the mass of a proton or a neutron is really basically 1 AMU, and there's only a tiny difference. These are easier to interpret. It's almost 1. An electron is a lot less than that. I think it's interesting to have real data. 0.0005486 AMUs. Grams are so small, it's really difficult to even comprehend. 1.673 times 10 to the negative 24th. There isn't even a Greek prefix for that. 1.675, it shows you how similar those two are in mass. Times 10 to the negative 24th. And electrons are 9, it sounds like it's bigger, it's not. 1.109 times 10 to the negative 28th. So it's really about 1,000. That's amazing. Okay. So that just gives you an idea of where those are. So these are the nucleons, these are the electrons, and to draw the picture, I think you've seen this before. I'm pretty sure this is on the timeline activity. Wow, terrible spelling today. I thought the coffee was kicking in, maybe too much. We use what's called the Bohr model, named after one of the physicists, Niels Bohr, another interesting character. Oh, I'm just doing a generic picture here. I guess I could do it for carbon. I'll just do a generic picture of a Bohr model. So a Bohr model is where you have the nucleus, really small. There's lots of different ways that analogies people use. Some people use an analogy of a giant stadium as the atom. The bleachers are the discrete levels, and a ball, I don't care what it is, a football, soccer ball, doesn't really matter, sitting at the very midpoint of the field, right in the middle, is the nucleus. And the rest is mostly dead space, but if you want a visual. Okay, so, yeah, so in the middle, you have your protons, you have your neutrons, and that's called the nucleus, discovered by Ernst Rutherford, the famous gold foil experiment, amazing experiment. It was just kind of happenstance. He moved the detector from behind the gold foil to the side, and he didn't expect to see anything. The particles ricocheted back because they hit the nucleus. Pretty cool stuff. Interesting history of science there. So that's Rutherford. And the nucleus could be stable or it could be unstable, which means it's radioactive. But we're not going to go into that right now. So there's the nucleus. And the neutrons in here were discovered by James Chadwick. They were neutrally charged, obviously, so it was a while before they were discovered. James Chadwick. So that's the nucleus. The energy levels we typically put, I'm going to draw them a little closer. I'll just do 3 because it's about all we're going to need. Are typically drawn like planetary orbits, just a way of visualizing it like this. And these are called energy levels. And we just number them, 1, 2, 3, etc. Starting from the inside, going out. 1, 2, 3. And they're discrete because this space is either here or it's here. It's not halfway in between. So an electron, if it's given some energy, some endothermic process, can jump from the first to the third or the first to the second, but it's not going to jump halfway in between. Or it can fall from the second to the first, which is an exothermic process, and that's how fireworks work. We can get to that some other time. And that's sort of the general model there. I think I actually do want to do carbon. And the first energy level can hold 2 electrons maximum. The second energy level can hold 8 electrons maximum. Just kind of remember that. So let's see. I'll do this up here. So for carbon 12, how would we draw the atom? Well, we would have 6 protons. 12 minus 6 is 6. We would have 6 neutrons. And that's really drawing it too big. We would have 2 electrons in the first energy level, and that's called a full energy level. And then we would have to have, well, 4 more out here. Okay, I might as well sneak in a few more things here. If you have a full energy level, it's completely full, there's no more that can go. These are called core electrons. They're very stable. It's a very stable energy level. Those are called core electrons. The electrons that are on the outside are called valence electrons. It's a Latin word, it means strong, it's just a historical word that's used. Those are the electrons that are most relevant to us as chemists. These are electrons involved in bonding, in chemical reactions. So those are going to be very important to us. So, oh, by the way, the core, the second energy level, if it's full, that would also be core, and the third energy level would be valence. And sometimes it's kind of hard to tell. And last thing I'll just kind of sneak in on you here is another symbol that we use for an atom is we put the element name, and we don't actually draw the nucleus, because at some point we're not going to really care about the nucleus. All we're going to care about are the valence electrons. So we do this. This is a little bit of bonus stuff. This is called a dot structure, or an electron dot structure, or a Lewis, named after the chemist who came up with the idea. Lewis electron dot structure, and those only show the valence electrons. The core electrons are not shown, the nucleus is not shown, only the valence electron and what atom it is. That's a very useful shorthand that we'll use down the line. And I think that's enough. I think that'll be enough for today. Actually, you know what? No. I'm gonna do one last thing. On the slides, and I'd like you to get your periodic tables out. Sorry, I'm fumbling around here a little bit. Letter F, atomic structure and the periodic table. Fine, you can write all that down, and you can find this in the book. I don't think we need to do this. You can actually take your periodic table and label it. So, the periodic table does a lot of work for you. If you look at an individual element square, you can get pretty much all the information for the most abundant isotope from that. If you know a little bit, you could then draw this picture, which I expect you to be able to do. So at this point, what I expect you to be able to do is if I give you an element, like oxygen, the sample problem, you should be able to dissect it. Tell me everything about it. And if I give you the percent abundances, calculate the average atomic mass. Okay, so the periodic table, here we go. I have no idea if you can really see this. So groups are what go up and down, and there's different ways to number these. We're going to use the new one, which is 1 to 18. Fine. The similar groups, they have the same number of valence electrons. Group 1 has 1 valence electron. Group 2 has 2 valence. They also have very similar chemical and physical properties. That's why they're called groups. And they have historic names, and you can write these down if you want to. Group 1 is called the alkali metals. Excellent. So, alkali metals. Group 2 alkaline earth metals. If this isn't making any sense, just go to your book. It'll have a picture of the periodic table. You can Google this. So alkaline metals, group 2, alkaline earth metals. The group kind of in the middle from, let's see, group 3 up until group, oh, I should know that, 12. Yeah, that's dumb, I should know that. So 3 up to 12. Those are collectively, you can even put a bracket here, called the transition metals. Okay. Group 13 is just called the boron group. There's no historical name. Group 14 is the carbon group. Group 15 is the nitrogen group. Group 16 has a name, but it's not really used. Group 16 are called the chalcogens. Mostly nobody calls it that. It's kind of an old-fashioned term. Usually it's just called the oxygen group. Then I think you might know the group 17, those are the halogens. Group 18 are the noble gases. Used to be called the inert gases, but they actually do have some reactivity. So you have groups going down the periodic table. Fine. Going across the periodic table are the periods. Whoops, maybe I should keep all of this. And what I would recommend that you do, so it's period 1, period 2, period 3. The period it's in, period means it's a recurring function like sinusoidal, because the properties change and they start over, properties change, start, that's why it's called periodic. Those correspond to the energy levels. So hydrogen and helium are in the first period, they only need one energy level. Group 2, you have the first energy level and the second energy level. So you fill that up. Then you go to the third. So the period number corresponds to how many energy levels there are in the electron. So you can actually label these 1, 2, 3, 4, 5, 6, 7. Whatever product you use 7 energy levels. But the period corresponds to the energy level. That's good to know. And then there's a dividing line between metals and non-metals. Most of the periodic table is are metals. And I don't think you can see it on this periodic table. Okay, well what I would do, maybe I'll do it on this one, is the metals, the dividing line is starting with boron, goes down, it's a staircase, goes down, over, down, over, down, over, down, over, and you have a dividing line between the non-metals, you can look this up in your book, the non-metals and the metals. That'll come in handy later, and I'm probably going to reiterate that when we get to bonding. So that's the periodic table and what it can tell you about an atom. I'm not sure I did a great job there explaining all of that, but the last thing I'll say here, because I think it'll help you with your homework, are, and we'll get to this later, are ions. Ions are charged particles. If I have carbon with a +1 charge, that means an electron has been taken away. One electron has been taken away. Carbon with a -1 charge means an electron has been added. So charge is formed on ions by either taking electrons away, and that's called a cation, or electrons being added to it, that's called an anion. So it has nothing to do with changing the nucleus. It's just electrons being taken away or added. Taken away, cation, because now the protons outweigh the electrons. Negative is an anion. Okay, that was just kind of an add-on there at the end. I think that's going to be enough to take us through week 2. Pretty short. We'll see. Maybe we'll go a little bit farther. But that's where we're going to end. This lesson was a little messy. Hopefully it's more organized in your notes and we can work on some problems in class. Okay, take care, and that's it for probably week 2.